Okay, so in this video, we're going to have a look at how to calculate float times and how to find a critical path. The float time of an activity is the longest time an activity can be delayed without impacting the minimum completion time. So sometimes we don't have to start an activity straight away. Instead, we can just wait a little bit before starting it, and we'll still be able to finish the project within the minimum completion time. Now, to calculate the float time of an activity, we use the formula latest start time minus earliest start time. So any float time greater than 0 means that the activity is non-critical, but usually if the float time is 0, it is critical. So let's have a look at some examples on how to calculate the float time of these activities. Using the formula LST minus EST, we know that the right number is the LST, the left number is the EST, the earliest starting time. So the float time is just 7 minus 3, which is 4. Because the units is days, it's 4 days. In question B, latest start time minus earliest start time. Because the units is hours, it's 0 hours. Question C, latest start time minus earliest start time. Units is minutes, so 11 minutes. Now the critical path is the path from start to finish where every float time is 0, but not every activity that has a float time of 0 will be part of the critical path. So you need to check by seeing if the earliest start time of the activity plus the activity's duration is equal to the latest start time of the next activity. So I'll be going through this with you just to make sure that you have the correct critical path. Most of today's questions will be coming from Ed Rollo, but I think that the guy made a few mistakes, so that's why I'm creating this video for you. So let's have a look at worked example 1. We have 4 activities for making an egg. What is the float time for each activity? So this is pretty simple. 0 minus 0 is 0. And this is all in minutes because here it says it's minutes. 3 minus 0 is 3. 7 minus 7 is 0. 6 minus 6 is 0. 2 minus 2 is 0. Okay, so that's done. Okay, so for activity A, that's activity A. Okay, that's for activity B. Okay, this is for activity C, etc. Alright, what is the critical path? So up here I said that the critical path usually is where every float time is 0, but we need to double check by doing the earliest standard time of the activity plus the activity's duration to see whether it equals to the latest start time of the next activity. So here I'm going to start with A. Does 0 plus 2 equal to 2? Yes, it does. So this A is part of the critical path. Okay, so we're looking at the early start time plus the duration to see if it equals to the latest start time of the next activity. So we're going to do the same thing again. Earliest start time plus the duration. Does that equal to the latest start time of the next activity? Yes, it does. So that is part of the critical path. And let's do that again. Earliest start time plus duration. Does that equal to the latest start time of the next activity? Yes, it does. So that's our critical path. From start to finish, it is A, B, D. Okay. Okay, worked example 2. The activities required to complete a physics project are shown in the network diagram below. All values are in hours. Find the float time of activity D. So here's the float time for activity, here's the EST and LST for activity D. Okay, it's always at the beginning of the activity. So the float time is just 10 minus 6, which is 4 hours. The length of activity C. Well, we know 4 plus something is equal to 12. Sorry, I shouldn't put this one. 12. So that has to be 8. Okay, activity C must be 8 hours long. What is the critical path? Okay, so usually, like I said, the critical path is when all of the activities have a float time of 0. So that's 0, that's 0, that's 0, that's 0. But let's just double check to make sure that it's correct. Okay, 0, earliest starting time plus duration, does that equal to the latest starting time of the next activity? Yes, it does. So B is part of the critical path. Try that again. Earliest start time plus duration, which we said was 8. Does that equal to the latest starting time of the next activity? Yes, it does. So C is part of it. And earliest start time plus duration, does that equal to the latest start time? Yes, it does. So E is part of the critical path. So we have B to C to E is a critical path, which basically means that once we finish activity B, we must start activity C straight away in order for us to finish within the 17 hours. Okay? Once we finish activity C, we must start activity E straight away in order for us to finish within the 17 hours. If we don't, it's going to take us longer than anticipated. Alright, I'm going to go through... Let's go through this one. Okay, so what is the critical path in the network diagram shown below? So this is from your textbook. So let's just write the float times for each of these. We know that's 0, that's 1, 2, 2, 1, 0, 5, 2, 0. Don't worry about that. 1, 1, 0, 0, and 0. So I see a lot of zeros. So let's have a look at this one. We have to do activity A. Okay. And here we can see we've got a 15, 15. Okay. But if I were to go through C, if I were to take my earliest starting time and my duration, do I get the latest starting time for C? No, I don't. Okay, 10 plus 3 is 13, not 15. So I can't go through C. Instead, 10 plus 5 is equal to 15, because remember, we have a dummy here. So technically, this is B. That is also activity B. 10 plus 5 is 15. Does that say 15? Yes, it does. So, activity B is part of the critical path. Next, earliest starting time plus duration. Does that equal to 19? Yes, it does. H is part of it. 19 plus 3. Does that equal to 22, the latest starting time? Yes, it does. So that's I is part of the critical path. 22 plus 4, is that the latest starting time for the next activity? Yes, it is. So L is part of the critical path. 26 plus 2, does that equal to the latest starting time? 28. Yes, it does. So M is part of the critical path. So here we can see that the critical path is from A to B to H to I to L to M, and that's it. Okay, let's do one more activity. One more question. Draw a network diagram for this project. So we have our start node that branches to A and B. Now A and B both go to C and D. Now remember, we're not allowed to have two edges that start from the same node and end at the same node. So instead, I'm going to create a dummy, but first I'm just going to draw in C. So here we can see that C is connected to A, but C is also connected to B. So I need to draw in my dummy. And C is 8. And both A and B are also connected to D. Let's draw that arrow again. Capital D, which is 7. We can see here that D is, oh sorry, I forgot to do this. Finish. So here we've got A, we've got B, we've got C, D, and E, but we don't have F, so it's going to finish at F. Okay. So we have C and D. Now we know D is connected to E, which is 10. And we know that C and E are both connected to F. So I'm just going to redraw my C like that. And they're going to be connected to F. And then I have my finish. Okay, so now that I've drawn my network diagram for this project, we can calculate the EST and LST for each of these. So I'm just going to enlarge this so I've got more space. Okay. So remember, we need to draw these boxes for each node, but at the beginning, at the very start node, if there's more than one edge coming out the start node, we need a separate box for each edge. Okay. So we're going to start with 0. In order to find the earliest starting time for activity C and D, we need both activity A and B to finish. So we need to take the largest time. 0 plus 6 is 6, but 0 plus 9 is 9. So we need to take the largest number, which is 9. So whenever we're doing forward scanning, we take the largest number. 9 plus 7 is 16. 16 plus 10 is 26, or 9 plus 8 is 17, so I need to take the largest number, 26. And 26 plus 12 is 38. And now we need to do our backwards scanning, where we go backwards. 38 minus 12 is 26. 26 minus 10 is 16. 16 minus 7 is 9, or 26 minus 8 is 18. I have to take the larger one, which is 9, the smaller one. Whenever we're going backwards, we're taking the smaller number. 9 minus 6 is 3, and 9 minus 9 is 0. So here we've got float times 0, 3, 0, 0, 0, 0. Now this is where I said we need to check, right? 0 plus 9, does that equal to 9? Yes, it does. So B is part of the critical path. Now, is 9 plus 8 equal to 26? No, it's not. So C is not part of the critical path, even though it looks like, because of the float time is 0, it looks like it is, but it's not. 9 plus 7, however, is equal to 16, so D is part of the critical path. 16 plus 10 is 26, so E is part of the critical path. And 26 plus 12 is 38, so F is part of the critical path. And that's my critical path. B, D, E, F.